Sri Gurubhyo Namaha children, welcome to our online teaching academy Ekalaiva. Today we are going to learn about magnetic effect of electric current. So already we were discussing about this lesson. So today we are going to talk about we are going to learn about electromagnetic induction. So when we hear this electromagnetic induction, obviously we should talk about a person. The name of the person is Michael Faraday. He is an experimental physicist and he had no formal education, and as well as in his early stages he was working in a bookbinding shop, and he used to read books which comes for binding, and that is how he creates, it makes he got interested in science, and because of that interest his contribution to science is much, and he made several path breaking discoveries that include electromagnetic induction and the law of electrolysis. So because of him only there is a very big huge development in electricity. Okay, so when we read this term electromagnetic induction, so we are going to induce something, and what he has induced, obviously he has induced current. How does it do? Okay. In our previous class we have discussed about electric motor, and we also know the principle of electric motor, that is Fleming's left hand rule. So what does this Fleming's left hand rule states? It states that when electric current and magnetic field, when they are perpendicular to each other, and obviously it exerts some force. Yes, and what this man thought is, what will happen if we reverse the concept? And obviously it works out. Okay, so what happened? He reversed it. That is what he has reversed. Magnetic field and the force, when we kept perpendicular to each other, will they produce the current? And obviously they have produced the current. So now let me do an activity so that we'll come to know how does this current has been induced. So for this activity we need three things. One is the galvanometer, and you know the purpose of galvanometer. Galvanometer is a device which is used to detect the presence of current in a circuit. And then we need an bar magnet, and also we need a circular coil. So what is the setup? Now we have to connect this circular coil, which has more number of turns, should be connected. Both the terminals of the coil should be connected with both the ends of the galvanometer. Once I have fixed, what I have to supposed to do is, we should bring the bar magnet, that is north pole of the bar magnet, towards the coil. So when we move that north pole of the magnet towards the coil, we will have some result. What is that? We can find a momentary deflection in the galvanometer. So what is that momentary deflection? So the galvanometer, the needle will be in the 0, it will go and it will come back in a fraction of seconds. So that is what momentary deflection. So when we move the magnet, it shows in the right side. And suppose if I withdraw the north pole of the magnet from the coil, there will be a momentary deflection, but now this time it will be in the opposite direction, that is left side. Not only the magnet, suppose if I keep the magnet stationary and if I move the coil towards the north pole of the magnet, and obviously there will be a momentary deflection in the galvanometer. And again, if I withdraw the coil from the north pole of the magnet, again we can find the momentary deflection in the galvanometer. So as I said earlier, galvanometer detects the presence of current. So when we move either the magnet or the coil, and obviously the current has been induced, that has been detected by the galvanometer. So now let me explain that observation. So you can find when we move the magnet into the coil, you can find the deflection, and when we withdraw the coil magnet from the coil, we can again find the deflection. And if we kept it stationary, what will happen? If we kept the magnet stationary, there will not be any deflection, no deflection at all. So only the magnet, either the magnet or the coil should be in the movement. And even if when you move the coil towards the magnet also, there will be a deflection in the galvanometer. So what are we going to conclude from this activity? The motion of a magnet with respect to the coil produces an induced potential difference which sets up an induced electric current in the circuit. So we know that when there is a potential difference, and obviously the charges in the coil will started to flow. So because of that, due to the magnetic field, change in the magnetic field, the current the potential difference has been induced. As a result of it, current has been induced. So this is what the electromagnetic induction. So this is we have done with the magnet. So in a particular situation, the magnet behaves in such a manner. So what is this lesson is about? This lesson is about magnetic effect of electric current. So what this magnet done now, the same thing should be resulted, that is same thing should be come from the electric current also. That means electric current also should behave in such a manner in a particular situation. Now let us explain you the other activity with the current. So for this, what I need is, I need two different sets of coils, coil 1 and coil 2, which is wounded in a cylindrical non-insulated cylinder. So this coil 1 should have more number of turns, so that it is called as primary coil. And the coil 2 should have a less number of turns, so we can name it as secondary coil. This primary coil should be connected with the battery and as well as the key. Both the ends of the primary coil should be connected with the battery and as well as the key. In the secondary coil, both the ends of the secondary coil should be connected only with the galvanometer. So what are we going to do here? I am going to switch on and switch off this primary coil by inserting and taking off the plug key. So when I inserted the plug key, what happens? There will be a momentary deflection in the galvanometer of the secondary coil, which is at the right side. And when I remove the plug key, and again there will be a momentary deflection in the opposite side, that is in the left side. But when I allow the current to flow through that by switching on, and there will not be any deflection. So the current will be induced in the secondary coil only when we switch on and switch off the primary coil. What makes the coil, current has been induced in the secondary coil means when we switch on this one, and we know that it behaves as a solenoid, and solenoid will have the magnetic field around it. So when there is a magnetic field around it, when we switch on, what happens? A EMF has been created. EMF means electromotive force. This electromotive force is nothing but it is the induced potential difference. So when there is an induced potential difference, and obviously charges will started to flow. So as a result of it, current has been induced in the secondary coil. So when there is the induced potential difference, only when you switch on the key and as well as when you switch off the key, because when you switch on only there will be a magnetic field will be produced. Same way when you switch off, again the magnetic field, there will be a change in the magnetic field. So that's all about this secondary, this one. So we can conclude that how the magnet behaves in a particular situation, same way current also behaves in a same manner. So what are we going to conclude from here? Okay, a potential difference is induced in the coil 2. How it is induced? Through the coil 1 changing, that is when we change the electric current in the coil 1, in the coil 2 current has been induced only when we starting and stopping, that is switching on and switching off. The current in the first coil changes the magnetic field associated with it, also changes. Thus magnetic field lines around the secondary coil changes. As a result of it, current has been induced. So far what we have seen, we can induce the electric current by two ways. So one is by moving the magnet, by moving it in a magnetic field, either the magnet or otherwise coil. When we move the coil or otherwise magnet, we can induce the electric current, and also by changing the magnetic field around it. That is the second activity what we have done today. Okay. So, and when does this induced current will be maximum? So when in Fleming's left hand rule, how this electric current and as well as magnetic field, when they are perpendicular to each other, the force will be maximum. Here also the same. So when force and as well as the magnetic field, when they are perpendicular to each other, that is at right angle, which means 90 degree. So you can see this current and as well as magnetic field, when they are at 90 degree, the force which is exerted will be at maximum. That is in case of Fleming's left hand rule. And here the magnetic field and the force, they are in the 90 degree, so that the current which is induced over here will be maximum. Okay. So now how can we find the direction of the current, in which direction this induced current has been produced? So in order to find that, let us read a rule called Fleming's right hand rule. So Fleming's right hand rule, what does it states? You are supposed to keep your right hand, the three fingers. What are those three fingers? The thumb, forefinger and the middle finger. These three fingers should be perpendicular to each other. So the same thing as we read in the Fleming's left hand rule. So the forefinger indicates the direction of the magnetic field and the thumb indicates the direction of the force when they are at right angle, and obviously the middle finger shows the direction of the induced current. You cannot mention it as a current, you have to mention it as induced current. So that's all about this Fleming's right hand rule. So this principle, where does it used? This principle has been used in the generator. So, generator, all the generators are working under this principle. So, when we keep the magnetic field and as well as the force perpendicular to each other, they will induce the current. And this rule otherwise called as dynamo rule. Why does it called as dynamo rule? You could have seen the dynamo in these cycles. Yes. So, actually it is a mini generator. So, what happens there? There will be a magnet inside it, and this dynamo, when we cycling this dynamo, the top part will have a contact with the wheel, so that it is also rotates. As a result of it, what happened? We are rotating the armature coil in between the magnetic field. So, when we do that, so what happened? It will create the electric current and it makes the bulb to glow. That's all about the electromagnetic induction, children. So, please do subscribe our channel to get the latest updates. Thank you, children.